As a bit of a 61C preview, let's talk about what it means to radix sort integers. So this is inspired by this question which Barack Obama was asked during the 2008 election.
Here at Google, and I like to think of the presidency as a...
So basically, Eric Schmidt here is asking Barack Obama
it's hard to get
about
a job,
things that seem important for the election.
Going through the rigors now. It's also hard to get a job at Google. Right. We have questions, and we ask our candidates questions, and this one is from Larry Schwimmer. Okay. What, you guys think I'm kidding? It's right here. What is the most efficient way to sort 1,000,000 32-bit integers?
Well,
I'm sorry. Maybe
no. I think
that's not a.
I think the bubble sort would be the wrong way to go.
All right. So anyway, so tried to gotcha Barack Obama, and apparently he at least knew a wrong answer. What is the right answer? Well, let's talk a little bit about leveraging the power of radix sorts. So as we know, estimating, like trying to answer the question that Barack Obama was asked, is pretty hard. If you want to know, is it better to use a comparison sort or a radix sort? Pretty tough because of all the issues we discussed, like the just-in-time compiler. But in the very large n limit, like lots and lots and lots of integers, the answer is actually easy. It's that radix sort is simply faster. So if we treat our alphabet size as constant, we know that LSD radix sort has runtime theta wn. And comparison sorts have runtime theta n log n. And so for sufficiently large n, if you can get enough integers, I mean, it's just guaranteed that LSD sort is going to be faster. So question, how would we LSD radix sort integers? We don't have any kind of character at method for integers, and we relied on being able to get the ith character for each digit, so to speak, of a string. So how would you do LSD radix sort on an array of integers? And I know that's kind of a vague question, but what would we need to do in order to make it possible to LSD radix sort integers? And basically the starting point is assume that you have some method that LSD radix sorts strings. What could you do? Okay. So my answers are, well, there's two things you could do. One, you could take the integer and convert it into a string. And if you do that, you're basically treating it as a base 10 number. Since the maximum Java integer is around 2 billion, then that means the W is going to be around 10. Okay, so every integer in Java, if you treat it as, you just convert it to the equivalent string, it'll be WN. The other approach would be, let's modify LSD radix sort to work natively on integers. Oh, and by the way, throughout this, I'm assuming our integers are non-negative. If it's negative, then we have to think a little harder. So everything here is non-negative. Anyway, so what we could do instead is modify our radix sort to work on integers, and basically instead of using char@, write a static method called something like getDefDigit. So you give it a number like 15,009 and say give me digit number 2, and it will give you back 5, or whatever syntax you want. Both of those approaches are reasonable, but this second approach gives you a little more flexibility and power. In particular, base 10 is not the only choice. So for example, we could take our number and treat it as another base. Now here we're straying into 61C territory. We haven't really talked about binary representation of integers and all that, but I still think this should be approachable, if maybe a little mysterious. So for example, the number 512,312, this base 10 number, it's 6 digits in base 10. But in base 16, it's a 5-digit number. The first digit is 7, the next digit is 13, then 1, then 3, then 8, similar to what we saw in our hashing lecture. So we'll note that this digit is greater than 9 right here, but that's okay because we're in base 16. This number could be anything between 0 and 15. Or if we go to base 256, now our number is only a 3-digit number in that universe. So it's base 7 is the top digit, 209 is the next digit, and 56 is the bottom digit. And these are greater than 9, but again, that's fine. We're in base 256. Okay, so a number can be decomposed into a base n integer in general. I won't talk about how that's done, but I just want to mention that it is possible, and it affects the number of digits you have. And you have this trade-off then between W, the width of each integer, and the size of the array we need to maintain the counts. So what would be the right base? Well, let's think a little bit about that trade-off. So if we say that our alphabet is of size 10, the numbers 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, then we have a base 10 number and up to 10 digits. If we say we actually have 16 possible digits, it's a base 16 number, and there's up to 8 digits. And I haven't proven that, but that's a fact you can show. In base 256, we have up to 4 digits. If we go up to base 65,536, now our count array will be pretty long. It's 65,536 entries long, but there's only 2 digits for each number. And you can go all the way up to some huge base. And in this case, we're treating the whole thing as a base 2-point-some billion number. And in that case, our number will always have exactly 1 digit, and we're basically just doing counting sort. Now, as you can imagine, the runtime depends crucially on the alphabet size. For example, if we pick this huge base, if we're doing counting sort, we know that'll be slow. We saw that in the previous lecture when we were trying to sort cities by their sizes. So some smaller number might be better, right? We know that this isn't optimal, and there's no reason to believe that 10 should be optimal. So I did a computational experiment to see what would happen, and that's another one that you can play around with if you'd like. This one's called timing test integers. And in this case, I compared quicksort to radix sort with various bases. So quicksort takes around 10.9 seconds on my computer to sort 100 million integers. But if I do radix sort, where I use base 16, so each number is no bigger than 8 digits, it's 3.6 seconds. Or I should say they're all exactly 8 digits. For LSD radix sort, we're just going to have a bunch of leading zeros. So if we had 8 digits, it took 3.6 seconds. If we had 4 digits, it was 2.28 seconds. And here, the only way to know is running these computational experiments. And so ultimately, what we get out of this is we've actually found a sorting algorithm that is faster than quicksort by a large margin for this number of integers. And so for a large number of integers, radix sort really is probably the way to go, because of the fact that it will be the way to go if we keep going bigger and bigger with n. Now you might ask, would MSD radix sort be better? Maybe, I don't know. You'd have to think about it. But I'm not going to talk about that in all in lecture. And this last example I show is the base you pick can actually move independent of the number of digits. So if we treat our numbers as base 1 billion, that's not big enough to push it down to a single digit number. But our counting array is so big, 1 billion in size, that now it takes 20 seconds to complete a counting sort because my computer had to build that giant array. Okay, so to summarize the answer to Eric Schmidt's question for Barack Obama, I think radix sort is a really good answer. There may be actually even better answers out there, but radix sort is even better than quicksort. I thought that's kind of cool. Now for a full treatment, to get a deep understanding of this number base and these digits and all that stuff, that's 61C's job. For here, I just wanted to give you an intuitive picture.